So cylindrical shells are just another way of finding volume. So in the past, what we've done, right, we've taken a region, we revolved it around an axis, true, and then we sliced it, right, into a bunch of little circular pieces generally, or rings, washers, right, circles cut out of them. We found the volume of each one, we summed them all together using an integral. Pretty straightforward. Pretty straightforward, Zin?
Yes.
Oh, wonderful. Okay. Now, this is a great method. It works for most of the problems that arise in calculus. It will work for every single problem on the AP test that you have to do volume, like, you'll have to do volume of a solid of revolution. If you're doing volume of a solid of revolution, then the disk washer method will always work. One of those will always work. But sometimes using what we call shells is easier. And what a shell is just a hollow cylinder. You can think about like an empty toilet paper roll or something like that. Right? Just like a hollow cylinder. And no top, no bottom to it, no bases. Just a hollow cylinder. And we should be able, let's just pretend like we've got one here. Here's a nice hollow cylinder. Okay. We should be able to find the volume of this cylinder. I'm going to give you guys a chance to write everything down. So just like listen for now, okay? And you can draw my pictures. So how do we find the volume of this hollow cylinder? It's what? It's like a rectangle. Yeah, basically that's basically correct. This, I mean, if you were to unfold it, it becomes a rectangle, right? So the problem is we don't really want to unfold them though. We want to leave them as they are. And so if we were to be able to find the area going around, which is I think what you're saying, right? You unfold it, and multiply by the thickness of this thing, we should be able to get the volume, right? Because it's got a very small thickness to it. So we take the area going around, multiply by the thickness, that should give us the volume of one of these little shells. Does that make sense? How do we find the area going around? Yeah, it's the circumference times the height. Exactly. What's the circumference? 2 pi r. So it should be 2 pi r h. That should be the volume. I'm sorry, that should be the area of this thing going around. The 2 pi r is your circumference times your height. And then the volume will be the thickness of it, which your thickness is going to be, I'm just going to write thickness, which is either dy or dx, depending on which way we're doing. And we'll worry about which way we're doing in a second. So the whole idea behind a cylindrical shell is suppose that this is the axis I was revolving something around, some region around, say it was the y-axis. We get this shell of one piece of it. And then inside of that, we get our toolbar. Not yet. Let's try again. Inside of that, that is maybe just slightly taller, there'll be another cylindrical shell that sort of sticks out of it. That is also hollow. It's stuffed right inside of it, right? And based on the nature of your function, maybe the region looked like, maybe the region looks like this, right? And so there's, it's getting smaller. Each of these cylinders is getting smaller as I go towards the y-axis. I might have another one inside of here that's even a bit smaller. It sticks out a little higher because it's up higher, but it's inside of it because it's a little bit narrower. And we might have some more of them that, came out here, right? We might have had some more that were out here that were beyond this and reach out to the edge of the region. And they all just sort of fit inside of each other, an infinite number of these little cylinders fit inside of each other. That generally makes sense what we're looking at here. The best analogy I've got for it is if you guys are familiar with Russian nesting dolls, you know what Russian nesting dolls are? Like those little toys that you might have had when you were a kid. You pop the head off of it, you decapitate the first one, right? And there's another one right inside of it. They're like the cannibalistic little decapitating dolls. And you take the next one out, there's a little one, you pop its head off and out inside of it. You take another one out, and right? Yeah? Familiar with those? Zoom? Familiar with those?
Yes.
Yes.
Zoom, good.
Yes.
Yes.
Good Zoom. There you go. Yeah, that was the first step. So good. You got to watch it in person happen. Patrick. Keep forgetting if you're Patrick or Jeremy. Patrick was very excited to hear me say Zoom good, good Zoom in person now that he's switched to in person. All right, so that's what we're going to do. We're going to take these shells, we're going to find their volume, the volume of one generic one. We're going to sum together them all. That'll give us the volume of the whole thing. Sound good to everybody? Okay. So this is the process. The process is graph the region. And here's my graph of my region. Ooh, look at that. There's my region right there, that line I did over there. Then what we do next is we sketch what we call a typical rectangle. So I would have sketched a rectangle like this. And then I would have revolved that rectangle around that y-axis, which would give me this cylinder that I first at the very beginning that I drew. And that just sort of gives you a sketch of what one of the cylinders look like, any generic one of them. And from there, you'll find the radius, you'll find the height, you'll figure out what the thickness is, and then you'll just do 2 pi r(h) times the thickness and integrate it from wherever to wherever based on the region that you have. Does that make sense? So that's what all this crap up here says. That if you want to write down now you have a chance to write down, but I figured it'd be better if you all look. Before you write all that down, that was fun. What's the thickness of this one? You can tell from the rectangle. So we always sketch the rectangle parallel to the axis that we're revolving around. And the narrow part of it is your thickness. So in this case, I wrote dy, but it's dx. dx, right? That's very thin in the x direction. And if I were to sketch my rectangle this way, I'd have to revolve it around something this way, right? Then that would be d1. Does everybody see that? All right, now you can write that. Okay, so oh, that's so fun. How much longer do you need? 20 seconds? 30 seconds? 45 seconds? From 7 o'clock this morning, still haven't finished because of this stupid math. All right, everybody good? Everybody got that down? Yeah. All right. Let's do a problem. We're going to start with one that it's already all drawn out for us because I just stole the picture from a textbook because I wanted to have a decent picture because I can't draw. This is a problem that we could solve using disks very easily. In fact, using shells for this one actually makes life a lot more difficult. But we're going to do it both ways just to see that it comes out to be the exact same value. And I think it'll help us to get the setup. And we're going to note a couple of important things as we go through. So we're going to take a look at the function y equals the square root of x from 0 to 4. And we're going to revolve it around the x-axis. And note that this picture, they tried to make it look three-dimensional in the textbook that I stole it from. So this is kind of like coming out at an angle. So it's trying to look like it's coming out of the screen at you. So we're taking y equals the square root of x and revolving it around the x-axis from 0 to 4. And what we would do is we would graph our function first. And the second thing that we would do is we would sketch what we call a typical rectangle, like I said before. And that typical rectangle would be parallel to the axis that we were revolving around. And you'd be able to look at that and you would immediately be able to say that the thickness of this is the y, right? Because the thin direction is in the y direction. And as we revolve that around and get this lovely little cylindrical shell that they'd already drawn for us, we would note that since we're going around the x-axis, the radius should just be the distance right here between the x-axis and that rectangle right there. And the distance between that rectangle and the x-axis is just the value of the just what? Yeah, it's just our function, right? Our radius is just our function. This is the cool thing about shells. If you are revolving around the x-axis, your radius will 100% of the time be y. If you are revolving around the y-axis, your radius will 100% of the time be x when you're doing shells. So that makes it easy. Your radius should be easy to find. Going around the x-axis, it's y. Going around the y-axis, it's x. Of course, that changes if we move the lines around, but that's fine. So our radius is just going to be y. And then the height is just the length from here to here. Well, that would just be the distance from the rightmost function. What's the rightmost function? X equals 4. So the height is just going to be the distance between 4 and the left function. Well, the left function, what's the distance that I've gone over here?
X.
I've gone over x, right? And x is equal to, we look at this, y squared. So our height is 4 minus y squared. So we've got our height, we've got our radius, we've got our thickness. That's all we need. 2 pi integral radius, height, thickness. Yeah. So let's write it out. We got 2 pi, we got the integral, we got our radius, which was y, we got our height, which was 4 minus y squared, we got our thickness, which was dy, and we need our upper and lower limits. And since we're doing everything else in this problem in terms of y, we need to have our lower and our upper limits also be in terms of y. So what's the lowest y value of this region? And what's the highest y value of this region?
2.
So we will do 2 pi times the integral from 0 to 2 of y times 4 minus y squared dy, which is easy enough. We just distribute and integrate, right? So let's quickly do that. 2 pi, 0 to 2, 4y minus y cubed dy ought to be integral of 4y is 2y squared. Integral of y to the third is y to the fourth over 4 and 0 to 2. If we plug in 0 to that, we know that's going to come out to be 0. So we'll just plug in 2. We end up with 2 pi times, now that's going to be 8 minus 4. Everybody good with that? Yeah, we're all good. Zoom, good?
Good.
Yes.
Good, Zoom. All right. Could we have done this using disks? The answer is yes, we certainly could have. And it certainly would have been a lot easier. And we're going to real quickly do that just for fun. Here's y equals root x. Here's x equals 4. Revolve it around. What do you end up with? You end up with a shape that looks like this, right? we would do pi times the integral from 0 to 4 of the radius. What would the radius be?
Y.
Just be y, which is root x. And since we're doing this as a disk, we would note that the thickness of each of these slices is dx. So our radius would be root x squared dx. And we'd really just be doing pi times the integral from 0 to 4 of x dx. Which would give us 8 pi. So we know that either way we do it, we get the same answer, which is good because it's the same solid. It better be the same answer. But the important thing to note here is that when we did it using disk, we used which variable? X. And when we did it using shells, we used y. So sometimes you will come across a function that is very difficult for you perhaps to convert back and forth between terms of x and terms of y. And suppose you were trying to go around the x-axis, but you were given a function that was in terms of y and you didn't want to convert it to terms of x, you could use shells. Or suppose you were supposed to go around, the y-axis, but you were given something, let's say, suppose you were given something, where you would have to convert it and you weren't able to convert it. It was impossible to convert it. Well, then that's fine. You could just use the other method that gave you the other variable. So it's convenient to know them both. Like I said, shells are not required on the AP test, but it's good to know how to do them just because you know how to do them for any future calculus. Yes. Yes. Well, if you're going around x equals -1, it'd be 1 plus x. Wait. And we'll do some of those. All right, so let's start with this. See if we can do this one here. The region, and I'm going to say, let's see. We got 4 minus x squared, right? That's that. We got y equals 3x. We're going to say the region in the first quadrant. Specifically, I just want to deal with the region in the first quadrant between this. So that'd be this region right here. X equals 0, 4 minus x squared, y equals 3x. We're going to revolve that around the y-axis. So if I want to revolve around the y-axis, I need to sketch my typical rectangle so that it is parallel to that axis. Everybody good with that? Zoom, good?
Good.
Good, Zoom. Rest of you good here? Parallel to the y-axis. So here is my typical rectangle. That's perfect. I revolve it around. Woo, exciting. All right. What is the radius? Actually, let's start with what is the thickness? Thickness is in the x direction. Yes, correct. So dx. It's very thin in the x direction. Thickness is dx. All right. Now, what is the radius? It's the distance from here to here. How far to the right did I go from the y-axis? What? Yeah, just that. I didn't hear what you said. That's why I said what. Just because I said what doesn't mean you have to question yourself. It just means that I didn't hear. The math covers my ears. That means it hurts me or something. We're just going to pretend that's true. All right, the radius is x. Everybody good with that? Yeah, wonderful. All right. What about the height? What? Yeah, the height should just be the upper function minus the lower function. It's just the distance between those two equations, right? The upper minus the lower. So the height ought to be the upper, which is 4 minus x squared, minus the lower, which is 3x. So we should get a set of the integral, 2 pi times the integral. Oh, we got to do our limits. We're doing it all in terms of x, right? So we got to do x values. What's the leftmost region, or left part of leftmost value of our region? 0. What about the rightmost value? Well, we got to figure that out. Right? We need to figure out where these two functions intersect. How do we figure out where two functions intersect? Set them equal to each other. If you had a calculator, you could do it with a calculator, but this one's easy enough to do without a calculator. It would be an x squared plus 3x minus 4 equals 0. And with any luck, y'all can factor that to x plus 4 and x minus 1. So where they intersect? They intersect at x equals -4, and they intersect at x equals 1. So what is the rightmost part of our region? 1. We got 2 pi integral 0 to 1, radius, height. Do we want to evaluate it? Are we okay with it? What is that? You're good? Yeah. I think we could distribute the x through and integrate. I mean, it's just a polynomial. So it should be pretty easy to do. Any questions there? Zoom, good?
Good.
Good, Zoom. All right, let's take a look at this one. I want to bound this by 2x minus 1, x equals 0, y equals 0, and also by y equals. I just want all well. We're going to say for, we're just going to make our lines easier. We're going to say for y greater than 0. Actually, let's just, yeah, we'll just bound it by all of those things. I'm going to add y equals 0. I don't think I needed x equals 0. I think I just wanted that to be y equals 0. That's fine. What's step 1? Graph it, okay? Graph it. 2x minus 1, something like that. Root x, something like that. X equals 0, that's not what I want. I actually want y equals 0. So I want to talk just about this region right here. That's what I want to do. Okay? We're going to bound it by, in fact, this will be better. Let's just do that. Sorry. I'm just going to do this real quickly. Y equals 0. Perfect. Problem solved. Okay. Now, what are we revolving around? Y equals -2. Here's y equals -2. Yeah? So I sketched my graph. What's the second thing I should do? Take the rectangle. The rectangle should be parallel to the axis you're revolving around. There it is. Woo. And we've revolved it around, and we've made a really, really beautiful cylinder. Yes? Okay. That cylinder has a thickness of dy, because it's in the y direction that it's right there. Okay. What is its radius? Now that we're no longer revolving around the x-axis, it's not just y. Right? Y is the distance from the y-axis to the function. Right? So what is the radius? It's y plus 2. Everybody good there? All right, now what is the height? Just like in the previous one, the height was the vertical distance between the two functions. Well, in this case, the height is now the horizontal distance between the two functions, right? So in order to find that horizontal distance, I need to figure out, let's see, this is x, we'll call it x2. This we'll call x1. Right? It should just be x2 minus x1, where x2 comes from the linear one, and x1 comes from the square root function. Okay? So we're going to say, how do I solve y equals 2x minus 1? X, that should be x equals y plus 1 over 2. Yeah. And y equals root x ought to be x equals y. So what does our height become? Which one minus which one? Y plus 1 over 2 minus y. And so our integral should be 2 pi times the integral. We got to do this in terms of y. So from the bottom of the region, which is 0, to the top of the region. Well, when do those intersect? When does 2x minus 1 equals the square root of x? Yeah, we could probably see that that's just an x equals 1, hopefully. Now, that's the x value of 1. Okay. Now, if I accidentally put that 1 up here, we got lucky this time because y equals the square root of 1, or it equals 2 times 1 minus 1, happens to be 1 anyway. But make sure that if you solve for the x value at where they intersect, but you need the y value, make sure you plug that x value into one of those original equations to figure out what the y value is. Doesn't matter which one, right? Because they intersect at that point, so it should be the same from both of them. So 2 pi times the integral from 0 to 1 of our radius times our height, d1. And you guys have mediocre algebra skills, so you should be able to distribute that all out and integrate. Everybody good with the setup? I'm not gonna spend the time distributing and integrating. Good? Zoom, good?
Yes.
Good, Zoom. All right. What about this? What if instead of revolving it around y equals -2, we revolved it up here around y equals 5? Would the thickness change? Nope. Thickness would stay as dy. Would the radius change? Yes. The radius would become 5 minus that little bit of y. So down here we'll say radius is 5 minus y. Does the height change? Nope. The height should stay exactly the same. So the only thing that's going to get altered, and the limit, like the limits of integration, will stay the same. So the only thing that's going to change here is we will replace the y plus 2 with a 5 minus 1. Good or no? Good? That's a thumbs up. Okay. You have curvy thumbs? Crooked. All your fingers are crooked. Weird. Yeah, that is crooked. Tori has crooked fingers, everyone. Just in case you were all wondering. You can't see. The rest of us here can see. My fingers are normal. Everybody good? Zoom, good?
Zoom good.
Good.
Good, Zoom. All right. Let's take a look at one more set of problems here with shells, and then we'll be done with shells. And then we should still have some time to go through some of the free response questions. I'll give you guys a second to draw your picture here and write it down if you wish, and then we'll go through it. What were you saying? Besides today's Monday, right? Besides today was Monday. Exciting. You see why we would, yeah? Yeah, it'd be really awesome. Yeah, so this is the whole point behind why I really think it's important to learn shells, because there are some problems that you just can't use discs or washers for. The AP test won't have any of those. You'll be able to use discs or washers for any of the solids of revolution on the AP test. But when you take Calc 2 next year, that won't necessarily be the case. So it's good to know how to use shells. Why couldn't I use a washer? If I were to try to take this region that I'm looking at, this region right here, and this is my region, and I want to revolve it around the x-axis, I'm going to get something down here that looks like that-ish, right, below the x-axis. And if I were to slice that, I would have to slice it vertically, which would mean it would have to be done in terms of x. Everybody agree with that? Yeah. It's got an outer radius and it's got an inner radius. If you all agree with that. The outer radius comes from the distance from the x-axis to the upper part of this, and the inner radius comes from the x-axis to the lower part of this. Well, the problem with that is that the upper part of that region and the lower part of that region are both defined by the same exact equation, right? And so you'd have to find a way to solve that for y, which I will tell you, in this case, it is possible to solve that for y and to write it out as multiple different functions, but it is not by any stretch of the imagination easy. And there are plenty of equations that you just cannot break them down because they are too complicated into different functions. So this is one we could not do in terms of x. It has to be done in terms of y. That makes sense? That you guys all see why it's important that we know how to do shells, even though it's not an AP test thing. Okay. All right. So if we're doing shells, we're going to, we need to sketch a typical rectangle. Doesn't really matter where, I'll just draw that one. That shows us that the thickness is dy, which is what we wanted because we decided we couldn't do it in terms of x. So a thickness of dy. And then our radius and our height. Well, we're going around the x-axis. So what's the radius going to be? That's going to be y. What about the height? It's just x, isn't it? Isn't our height just x? Just the distance from the y-axis to the function, x, which is 12 times y squared minus y cubed. So really using shells, this is pretty straightforward. The function is just the height, radius is just y, thickness is dy. All you got to do is, I'm going to pull the 12 out. So I have 24 times. We have an integral from 0 to, where does that intersect up here with the y-axis again? X equals 0 and 12 times y squared minus y cubed equals 0. Right? That's when 0, x, that's our y, 0 and y is 1. Squared minus 1 cubed is still 0. 0 to 1. And we've got y times y squared minus 1. Any questions on that? Relatively straightforward. What about if we decide to move it around the line y equals 1 instead of around the x-axis? Would the thickness change? Just the what? Just the radius. Everything else would stay the same. The thickness, the height, the limits of integration, everything would be the same. All that would change would be the radius. And what would the radius if we were going around y equals 1 be? Just be 1 minus 1. What if I went around the line 8/5? What would the radius be? 8/5 minus 1. Would anything else change? Would the thickness change? Would the height change? The 2 pi, the limits of integration, the fact that there's actually an integral there, would all be the same. So this should just be 24 pi integral 0 to 1 minus 1 and y squared minus 1. This would be 24 pi 0 to 1 8/5 minus 1 y squared minus 1 cubed d1. What if it was around the line y equals -1? How would the radius change? It'd be 1 plus. This one seems like a stupid one. Why would I put 8/5 on there? The reason being because that integral turns out to be 2 pi. And usually I finish and say, look at that, we did all of this, and our last integral here was 2 pi, and it's really exciting, and everybody's like, 2 pi. It's 2 pi. The end. That's it. That's shells. That's the concept of shells. It may help you on the AP test if there's a problem that you could use it for. It may not be shells. Who knows? But at least now you know. Anybody have any questions on shells? Yeah. Nope. You don't have to. I'm going to post an assignment with, I don't know, 6 or 7 shells problems for you to do.
Wait, so if the axis of rotation was y equals -1, what would the interval be again?
The radius would just change to 1 plus y, but everything else would be the same. What was that? Was that a uh-huh? Or was that a huh?
Yeah, thank you.
Yeah, no problem. Yeah. I will not put shells on any quizzes. I will not require you to know it. So if you want to completely forget everything we just did about shells in the last 40 minutes, that's fine. Yes? No, you can still use it for those ones. Like, for example, because like I said, like you're talking about, going around y equals 1, right? That's that way. If we were doing it in terms of x, those would be washers, right? Right. And here, because we're integrating from 0 to 1, that still takes care of every, I mean, this is not fully pushed up against it, but that's fine because the closer it gets, we get, get that little gap in there. The gap is built in, so it's like we revolve it around. It's shorter, like it's on the inside, like those very narrow ones. It's shorter than the full length, so it doesn't take up the whole. Does that make sense? It's hard. It's kind of hard to describe, but it takes care. Yeah. All right. Anybody else? Any other questions on the shell stuff? Are we missing? Who are we missing? That's supposed to be. Oh yeah, Philip. Oh yeah, Philip. Philip's not here. That's who's supposed to be here. Okay. All right. Let's. What?
I miss you guys. Hi.
Tom says he misses you too, but nobody else said it. I don't know. I don't know how you feel about that. But all right. Next thing we're gonna do here, real quick, is look at all those notes. No, I don't want that. No, that's not. I want this one. Okay. Give me 1 second here. I had you guys do some of these area and volume FRQ problems over the weekend. You're supposed to do some of these? Yes? This first one here was a non-calculator problem. This was the very first one in the packet that I asked you guys to do. Did you guys do these or no? You what? No? You did not? Some of you did not do these? You attempted some of them. Okay. You will find that generally in the area volume there are, I want to say you should know what to expect for an area volume problem going into the AP test. Generally, part A is find the area of some region. And generally, parts B and C have to do with finding some sort of volume. Usually, one of them is like the cross sections are these weird shapes, or the cross sections have this specific area. Find volume. That's like the very beginning volume stuff we did, where we had to find like the volume of a square and integrate it across the volume of an equilateral triangle, or the volume using an area of 1 over x plus 3 as the cross-sectional area. And then the last part of it is usually the volume of some sort of solid where you revolve it around. Yeah, or B and C might be close. But usually 2 volume pieces, 1 area piece. So if you haven't done it, that's fine. If you've done it, that's great. We're going to go through it anyway. You should have done the first 6. If you haven't done the first 6, try and get through the first 6 by tomorrow. So we'll go over a couple of them tomorrow, but I also want to get into some other types of free response, especially for the May 4th test people. So we want to find the area of region R. So you guys okay with that? You guys all right? Yeah. Okay. All right. We're going to find the area of region R. So in order to find the area of region R, we need to find the upper function and the lower function, and we need to subtract them and then integrate, right? What's the upper function? Is it g of x or is it h of x?
H of x?
Yeah, it should be h of x, right? Because that one's a parabola, and this one is clearly not a parabola. That looks more like a trig function, right? So we are going to, for A, we're going to integrate h of x minus g of x dx from 0 to 2. Everybody agree that it should be from 0 to 2? So we'll do that on the next page where we have some more room. And I don't remember any of the functions. Negative 2 plus 3, no, 6 minus 2 times x minus 1 squared. Minus, what's that? Negative 2 plus 3 cosine pi x over 2. All right, so we need to integrate this. Let's simplify it a little bit first. Seems good. If you want to distribute out the x minus 1 squared, you can. If you don't, then you want to just do like a little substitution on that for the integral, you can. You guys want to distribute it out, or what do you want to do? You want to do the substitution? Okay. So before we do that, first off, 6, and then the minus the negative 2 ought to be an 8. So we can make that an 8 minus 2 times x minus 1 squared minus 3 cosine pi x over 2. Everybody good with that's the sort of simplified version of that? All right. Integral of 8 is 8x, right? How do we deal with the 2 times x minus 1 squared? Or even just the x minus 1 squared? Right? If I have x minus 1 as my u, then that would become negative 2u squared, which is easy to integrate. And the du, in this case, is just dx. So anytime it comes out that the du is just dx, conveniently, you can just integrate and plug that x minus 1 back in. So this should become negative 2/3 of u cubed, or minus 2/3 of x minus 1 cubed. Everybody good with that? You guys all hear all the fun sounds that the computer made? Yeah, good for you. Okay. Then for 3 cosine pi x over 2, what's the u substitution going to be? pi x over 2, yeah. So du will be pi over 2 dx. So that means that within the integral, we got to put in a pi over 2. And outside the integral, we got to put a 2 over pi. So we're going to effectively have a minus 6 over pi, right? 2 over pi times the 3, and it was a minus before. And then cosine of u, what's the integral of cosine of u? Sine u, and u was pi x over 2. Everybody good with all the integral there? Yeah, Tom. You're splitting it into 3 different integrals technically and doing a different u sub for each one. Unless you just sort of off to the side, think about it and then just write out the answer like I did. Yep. In fact, you don't have to put it all back together if you don't want to anyway. You can leave it as 3 separate integrals and then evaluate each one and then add them together. But yes, that is effectively what you're doing because the u sub that you need for the middle piece is not the same as the u sub you need for the last piece. Yep. All right, so now we'll evaluate at 0 and at 2. So at 2, we got 16 minus 2/3 minus, let's see, this becomes the sine of 2 pi over 2 or the sine of pi. What's the sine of pi?
0.
And then we got minus. If I plug in 0 here, I get 0. Plug in 0 here, I get negative 2/3. So that should become a plus 2/3. Yeah. And then sine of 0 is 0. So we end up with 16 minus 2/3 minus 2/3. 16 minus 4/3, which ought to be, I believe, 44/3. Everybody good there or no? All right. I should have pulled up the scoring guides. I didn't pull up the scoring guidelines. That should have been worth 3 points. 1 would have been for the final answer. 1 would have been for the right setup, and 1 would have been for the right values of the integral. Good or no? All right, for part B says region R is the base of a solid, and for each solid at each x, the cross section perpendicular to the x-axis has an area of 1 over x plus 3. So this is not a solid of revolution, is it? It didn't say we're revolving around something. This is a cross-sectional area problem. And what was the formula that we used? 0 to 2 in this case. We just needed to integrate, when we did cross-sectional area, the area, right? In this case, the area dx. Well, they told us straight up what the area is. They didn't say cross sections are squares, and then we had to find the length of one side of the square and then square it for the area. Or they didn't say that cross sections were semicircles, and we had to recognize that the length across the region was the diameter and take half of it and then do 1/2 pi r squared with that. No, they gave us the area. That's all we got to do. We just got to integrate 0 to 2 of 1 over x plus 3 dx. It's literally all we have to do. Okay. You would have gotten 1 point for that. You would have gotten 1 point if you successfully integrated that. That requires a u step, right? U is x plus 3. But du is just dx. And when du is just dx, you can just treat this as if it was 1 over u immediately. So that's the natural log of the absolute value of u, or natural log absolute value of x plus 3. Which is the natural log of 5 minus the natural log of 3. You would have got 1 point for that and 1 point for that. You could also have said it's the natural log of 5/3. That'd be fine too. Either way. Any questions on part B there? All right. And then the last part, part C, said something about revolving it around y equals 6. We're going to revolve around y equals 6. We're going to have an outer radius and an inner radius, right? This is going to be washers. So what's your outer radius? What's that? Not quite. It comes from h of x, but it's not h of x. Actually, it doesn't. Actually, it doesn't come from h of x. It comes from g of x. Right? It's the distance between y equals 6 and the lower function. That's our outer radius. Yeah. So what should that radius be?
6 minus g of x.
Minus g of x. And our inner radius ought to be 6 minus h of x. And if this is the AP test and they've defined these as g of x and h of x, you can just use g of x and h of x because it says, right, but don't evaluate, so you don't even have to do the integral, right? Just have to write the integral itself. So you can say I times the integral from 0 to 2 of 6 minus, now I forgot, was it g of x or h of x first? G of x was the outer radius. And that's it. Pi times the outer radius squared minus the inner radius squared, integrated from 0 to 2, dx. Doesn't say to evaluate. Don't bother to simplify. Don't bother to integrate. Don't bother to evaluate. It says write, but don't evaluate. Just write this. This is perfect. Good? Any questions on that? All right. I asked you guys to do this one, yeah? How'd this one go? Yeah, they threw in some extra stuff in this one. That's not good because you only have an hour to do all of the non-calculator free response problems. All right, so we are given a funnel. We are told that the height of that funnel is 10 inches. It has circular cross sections. Okay, we can see that. And we are given that any height h, the radius is given by this formula. We want to find the average value of the radius. Well, how do we find the average value of a function?
The mean value theorem.
Yes, the mean value theorem for integrals. That will always give us the average value of a function. So for part A, the mean value theorem for integral says 1 over b minus a, right? So what is b minus a?
10 minus 0.
10 minus 0, because we're going from 0 to 10. Times the integral from 0 to 10 of the radius function, 1/20th of 3 plus h squared dh. So that's your integral setup for the average value of the radius of the funnel. The 10th times the 20th is 200. And so then we're going to integrate 3 plus h squared to become 3h plus h cubed over 3 from 0 to 10. And that gives us what? 1 over 200 times 10 plus 1,000 thirds. Yeah.
Is 30 plus 1,000 thirds?
Oh, yeah, 30 plus 1,000 thirds. I could multiply 3 by 10. That'd be good. And then we just simplify. Yeah. What do you get if you simplify that?
Uh, 109 over 60 inches.
Over 60. I said 60? 109 over 60 inches. Cool. There's your average value of the radius. Make sense or no? Okay. What if we want to find the volume of this? Well, we sliced it horizontally, right, to get circular cross sections. Okay. We sliced it horizontally. The thickness would be dy normally, but what is our y-axis defined as?
H.
H. So we'll say that the thickness will be dh. Okay, and so all we have to do then is, for part B, pi times the integral from the bottom to the top, which is 0 to 10 of our radius. Well, our radius is r squared. So 1/20 and 3 plus h squared. Squared dh. Good with the setup there now. Yeah. 1/20 times 1/20 is 1/400. We can bring that out front. Pi times pi over 400 times the integral from 0 to 10. If I distribute 3 plus h squared out, what does that give me? 9 plus 6h squared plus h to the 4th. And then you just integrate and evaluate. Pi over 400. 9h plus 2h cubed. And then plus h to the 5th over 5. Good or no? Okay. So what does that give us? Pi over 400 times 90 plus 2000 plus, geez, what does that come out to be?
20,000.
20,000? Yeah, that sounds right. 100,000 divided by 5. And it's all minus 0 at the end. So we end up with 22,090 pi over 40 times over 400, or 2,209 pi over 40. Good or no? Any questions or issues there? All right, part C says the funnel contains liquid that is draining from the bottom. At the instant when the height of the liquid is 3, the radius is decreasing at 1/5 of an inch per second. What is the rate of change of the height of the liquid with respect to time? So this is a related rate problem. We are given h equals 3. We are given dr dt is negative 1/5 because it's decreasing, so that's why it's negative 1/5. And we want dh dt. Well, we have the function r equals 1/20 of 3 plus h squared. So if we know the height that we're looking at, and we know the dr dt, and we want the dh dt, all we need to do is take the derivative of both sides with respect to t. So the derivative of r with respect to t is dr dt. And the derivative of 3 plus h squared is 2h dh dt. Everybody good with that? What was dr dt? Negative 1/5. And what was h3? So what do we end up with here? Multiply by the 20 gives us negative 4 over here. Divide by the 6 gives us negative 4/6. Negative 2/4. And our units would have been inches per second. Good or no? Yeah. That one's a little bit of an abnormal area type volume FRQ, but it's good to see this. From here to here, we took the derivative of both sides with respect to t. So the derivative of r is dr dt, and then the 1/20 is the constant, so stays, and then 3 is 0, h squared becomes 2h, and then dh dt. Does that make sense? All right, I think that's probably good since we have like less than a minute to go. Anybody have any questions on anything here in the class or in Zoom? Zoom, good.
Yes.
Good, Zoom. You have this one problem from that book, okay? Demonstrate Rolle's theorem using what? You need to, I don't know what 3 things it's saying, but I assume that yes. I'm gonna stop recording because nobody can see what I'm talking about now.